In this video, we're going to look at a concept called electron configuration. You would learn about this concept early in your high school chemistry class in Unit 1. Electron configuration shows us how the electrons are positioned around the nucleus of atoms, and the electrons are on the outside of the atom's nucleus. And so electrons are really important because they are the ones that participate in chemical bonding. So if you understand the electrons that are in hydrogen and the electrons that are in oxygen and how they're positioned, then you can understand how chemical bonds are formed between hydrogen and oxygen to make a compound like H2O or water. So this is one of the building blocks for chemistry, electron configuration. Very important, very foundational, and kind of unlocks the keys to our chemical bonding unit. So by the end of the video, I want you to be able to predict the electron configuration of atoms using the periodic table as a model, and then use electron dot structures to represent an atom's valence electrons. So if we take our first element number 1 on the periodic table, hydrogen, and then we'll take a look at helium. And then we'll take at element number 3, we'll look at lithium. Just kind of take these first 3. So first thing we got to understand is that atoms have a nucleus. And in the nucleus are protons and neutrons. And these make up the mass of atoms. So this is where all the mass comes from. And then on the outside of the atoms are the electrons that are moving very fast, and they're very, very tiny, and they do not take up any mass of the atom, but they are important because they participate in chemical bonding. So that's why we need to know here the electron configuration, where are those electrons located. So if you look at the periodic table, you'll see that hydrogen has an atomic number 1, and so it's got 1 proton. Let's make it protons are positive, so it's got 1 of those, P for proton, and it's got 0 neutrons. And then hydrogen has, let's just call this the nucleus. And so then we'll draw one ring of electrons, and then let's just make this orange one. This will be on our electron and has a negative charge. So hydrogen has 1 electron and 1 proton. So that's the atomic structure or the Bohr model of hydrogen. Now when you go over to helium, helium has 2 protons. That's a tough one. Try my best here. So it's got 2 protons or positive charges, and its mass, it has an atomic mass of 4. So mass is equal to protons and neutrons. So if the mass is 4 and the protons are 2, it must have 2 neutrons as well. And neutrons don't have a charge, they're neutral. So that means it has 2 electrons. So one ring of electrons, and then let's do 1, 2 electrons. So that's the atomic structure of helium. And then for lithium, element number 3, It's got 3 protons that are positive, each positive charged particles. It's got an atomic mass of 7. And so it has 3 protons, so that must mean it has 4 neutrons. And I'm just getting the mass from the periodic table. And then let's draw our rings here, or our energy levels. 1, 2, because lithium's in row 2 of the periodic table, and we'll talk about this here a little bit more in a few minutes. So it's got 1, 2 electrons in the first energy level, and then it's got a third. So lithium has 3 electrons. Helium has 2 electrons. I can't spell. And then hydrogen has 1 electron. So this video is about where those electrons are positioned around the nucleus. And remember, the nucleus is this inner space where the protons and the neutrons are located. And then we have rings, or energy levels. And those energy levels are the distance the electrons are from the nucleus. So why is that important? Why is it important to know where the electrons are located? Because when the atoms come in contact with each other, so if lithium were to come in contact with, say, hydrogen here, it's this outer ring, these 2 outer rings. These are the electrons that come in contact with another atom first, that participate in chemical bonding. And so it's really important for us to know where the electrons are located. So this electron here that hydrogen has in its most outer ring is called the valence electrons. And you can see that hydrogen has 1 valence electron, 1 valence, and it only has 1 electron. So its outer electron, its 1 electron is its valence. Lithium is actually has 1 valence electron as well. And then helium has 2 valence. So because atoms have different valence electrons, they behave differently and they interact differently and they bond differently with other elements on the periodic table. So it's really, really important that we understand this concept. So a couple words you need to know for electron configurations are energy level, sublevel, and orbital. So in energy level 1, you have the S sublevel, and then you have the 1s orbital, in energy level 2 you have the s sublevel and the p sublevel. you have the 1s orbital. Sorry, I didn't mean that. You have the 2s orbital. And then you have three 2p orbitals. So the sublevels are the S sublevel, the P sublevel, the D, and the F sublevel. And then the sublevels are further divided by orbitals. And there's S, P, D, and F orbitals. There's only one S orbital per sublevel. There are 3 p orbitals per sublevel. There's 5 d orbitals per sublevel. And there's 7 f orbitals per sublevel. So the orbitals are more specific areas where the electrons like to hang out. The sublevel is a little larger than that. And then the energy level is the general distance from the nucleus that you are. And so it gets more specific as you go down towards orbital. So let's do an example here. So in lithium, there's 2 energy levels. So you have energy level 1 and energy level 2, which are the 2 green rings outside the nucleus. And then energy level 1 is a little bit closer to the nucleus than energy level 2 is. Now you'll notice in energy level 1, there's 2 electrons that are situated in this first ring right here. And so we would write a 1 for energy level 1 if we were writing its electron configuration. In the first energy level, you have the S sublevel, and you only have the S orbital. You only have one S orbital in that sublevel, and there's 2 electrons that can occupy that S orbital. So we write 1s2, and you'll notice there's only 2 electrons in lithium in the first energy level. Now, once you move to the second energy level, you put a 2 for second energy level, and you'll notice that in the second, well, it's hard to show it here, we'll see it on the periodic table, but in the second energy level, you start with the S sublevel again, and there's only 1 S orbital in that sublevel, and you can fill 2 electrons in the S orbital, but lithium only has 3 electrons total, and you can see there's only 1 electron here in the second ring, so we put a 1 to represent this 1 electron, and then these 2 electrons you can see here, right, are represented by this 2 here. So we're telling somebody where those electrons are located outside the nucleus. And remember, this number here is the energy level. Right, is the energy level. And then this, for us, we'll call the orbital. And then the number is the electrons. And so all three of these have to be represented in the electron configuration. And we would call this, if we wrote this, we'd call this whole thing right here, this is called an electron configuration. It's a little code to show people where the electrons are located. All right, so let's do a little breakdown of sublevel to orbital. So you got the 1s sublevel, and you have the 1s orbital. You have the 2s sublevel, and you have the 2s orbital. When you have the 2p sublevel, you actually have 3p orbitals. So maybe better if I kind of show these with little orbital diagrams. So let's say we call these boxes the orbitals. So in the 1s orbital, you can hold 2 electrons. And let's make each arrow represent an electron. In the 2s orbital, you can hold 2 electrons as well. But when you have the 2p orbital, you actually have 2px, 2py, let's say 2pz. So you have one, 2, 3 orbitals, 3p orbitals. So 2px, 2py, 2pz. And so you can hold 1, 2 electrons in the 2px orbital, 2 electrons in the 2py orbital. Oh, it's terrible, but moving on here. And then you have 2 that can go in the 2pz orbital. So this is interesting because although there's only one 2p sublevel, there's one orbital here, one orbital here, and one orbital here. Now when you draw this, remember these are in 3-dimensional space. So that's one orbital, two orbitals, three orbitals. So you got the 2pz, 2px, and then the 2py. So the vocabulary gets a little confusing because we have these sublevels, but then inside the 2p sublevel, there's 3 2p orbitals where electrons can hang out. And so when you get into if you looked at the D, let's look at the D. So the D orbital can hold, so you can have 1, 2, 3, 4, 5 d orbitals. So D, 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 D. So you can have 5 d orbitals. And then if you kind of do the numbers on that, right? So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, and then if you were to do, well, if you just look at these 3 here, how many electrons are in an s orbital? 2 electrons. How many electrons are in the p sublevel? So there's 2 electrons in a p orbital, but the p sublevel, the p the 2p sublevel can hold 6 electrons. And then this the d orbitals, all 5 of these d orbitals can hold up to 10 electrons. So 10, 6, and 2. And we're not going to get into the F, but the F orbital can hold up to 14. The F orbitals can hold up to 14 electrons in that sublevel. All right, so where are the energy levels, the sublevels, and the orbitals located on the periodic table? So this is how I use the periodic table to do all my electron configurations. So you have energy level 1. Let's do those in a different color, actually, just so that you can we can see them. So you have energy level 1, energy level 2, energy level 3, energy level 4, energy level 5, 6, and 7. So there's 7 rows on the periodic table, or periods, and those correspond to the 7 energy levels of electron configuration. And then this here is the S block. So these first 2 columns. Oh, this is going to be tough here to get that all the way listed. This is the D block. And then this is the P block. Except for this helium, this one's part of the S block. And then the F block, I'm not going to get too much into it, but this cutout down here, those 2 rows that are cut out, those are where the F orbitals are located. And so if you understand the periodic table, you can kind of read this like a book. So let's do the first one, and let's do like a red color. So energy level 1. So this is the 1S1, because it's the first energy level. So we have a 1. It's in the S block. So it's an S sublevel. And there's 1 electron for element number 1 on the periodic table. We go over here to the right, we're going to move left to right like a book. So we're going to end up straight across. So over here we're in energy level number 1 because we're still in row number 1. And we're in the S block, but we're the second element in now. Element number 1, element number 2, so 1S, 2. Then we go down here to energy level 2. Now we're still in the S block, but we're in row 2. So this is a 2S1, which makes this a 2S2. Now, when we move to the right, you'll notice there's a lot of empty space here. And when we get over here to element number 5, we're actually in the P block. So this will be a P. But what row are we in? We're in row number 2. So this is a 2P1, and then we go 2P2, 2P3, 2P4, 2P5, and 2P6. And then we're going to go down here to row 3. And we're back in the S block. So it's a 3, it's a 3S1 and a 3S2. And then we're going to head over, empty space here. We're going to head over to element 13. That'll be 3. Why is it a 3? Because above us was row 2, but now we're in row 3. We're one element in the P block. So it's a 3p1, it's a 3p2, 3p3, 3p4, 3p5, and a 3p6. And then we're going to, like we're reading left to right, top to bottom. So we're going to go down to row 4. We're in the S block now again. So it's a 4s1 and a 4s2. So you can see the S block above it, 4s1, then above it is 3s1, above it is 2s1, above that is 1s1. Okay. Now when we go to the right here, we actually enter the D block, and this is a really frustrating part of the periodic table because the D block actually turns into, even though we're in the 4th row, this becomes, I didn't want that. This becomes a third energy level. So this is a 3. The D block starts up in the 3rd energy level, and there's some orbitals that are available in the 3rd energy level, not the 4th. And so it's a common, frustration, a little bit, a mistake that students have when they start out with this. I know I don't like that it's the 3 here either because it's in the 4th row, but it is. You got to remember to go down 1 when you're in the D block. So it's a 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, and 3D10. And then once we pass the 3D10, element number 30, we're back in the P block. So remember, the P block, it's right here. Here's the P block. So, and then the D block is to the next to that, and then the S. The S is right here. It's frustrating. I don't think I'm going to be able to draw this. I don't know why that's being a pain. But now you have the P block to your right. So we're in the 4th row. So it's a 4p1, 4p2, 4p3, 4p5, sorry, 4p4, 4p4, 4p5, and a 4p6. And we could keep going. Let's just kind of do one set here. So this is a 5s1 and a 5s2. And then we go to the right, and we're in the 4th. So this is a 4d1, 4d2, all the way out to 4d10. And then this is a 5p1. This will end up at a 5p6. So this is a 6p6, 7p6. And then this is a 7s1. This is a 7s2. So, if we could follow the pattern, we could write all these out. We're not going to write all these out, but you should be able to generally go in and fill out the pattern here for all these. This is the general setup here for electron configuration. All of the energy levels, the sublevels, the orbitals are really built into the periodic table. Its shape, which allows us to master the location of electrons, which allows us to learn how chemical bonding occurs. Down here at the bottom, let's see if I can zoom out here. So once you leave, you see 6s2 here, element 56. Once you go to element 57, you actually take a little detour. So after the 6s2, the 6s2 then becomes this F block. Starts at the 4th, so it's 4f1, 4f2, all the way to 4f14. So 4f14, and then this will be the 5f1, and this will be 5f14. So the f orbitals don't start until the 4th energy level. I know it's hard to remember that, right? Like the D start at the 3D, the F start at 4F. So after you leave element 56, the 6s2, then you would go 4f1, and then after you leave 7s2, then you would go 5f1, because after element 88 is element 89. So that's just a little more challenging. You don't typically do a lot of F orbital configurations in chemistry 1 usually. So then let's kind of take a look at this in terms of like our count. So the S, the P, the D, and the F. So the S sublevel can hold 2 electrons. And the P sublevel, which includes, like if you look at the 2p, it has up to 6 electrons. And then the D block, the green, can hold up to D10. And then all the way at the bottom, the yellow-orange, is the F block, can hold up to 14 electrons. So the S sublevel holds 2 electrons. It's got 1 S orbital. The P orbital, you have 3 orbitals here. So you have 3 orbitals. 3 orbitals times 2 electrons in each orbital is 6 electrons. The D sublevel has 5 orbitals. 5 orbitals times 2 electrons can hold 10 electrons. And then the F sublevel has 7 orbitals that can hold 2 electrons each. That's 14 electrons. So we'll do another video where we'll write the electron configuration using orbital diagrams. All right, so let's write the electron configuration for an element now that we have that order on the periodic table. So let's do hydrogen. So hydrogen is first energy level. This is the S block, and it's 1 box in, so it's 1s1. We'll do helium. That's in the first energy level right here, and it's in the S orbital, S block, and it's 2 electrons in, so it's 1s2. We do lithium. So to do this one, we have to build it from the ground up. So lithium, we start here, first energy level. The S orbital can hold 2 electrons. So that's going to be 1s1, 1s2. And then when you get to lithium, that's going to be 2 2s1. So its configuration is 1s2, 2s1 to get the lithium. Now, if we're doing, let's do beryllium, which is right next to it. So beryllium would be 1s2. Let's go back here and let me show you. Let me like rewrite this up. So if this is let me erase this. Just start over here with this. So if we're doing beryllium, beryllium is right here next to lithium. So let's start from the beginning. So 1s1, 1s2. So that's the first one, 1s2. And then we go down to the second energy level, 2s1, 2s2 is filled. It's 2s2. And so that's 4 electrons, and we're done because we're at beryllium. And we count our electrons. 2 and 2 is 4, and we have 4. Then if we're going to go to boron, boron is just going to be 1 more electron than beryllium. So it's 1s2, 2s2. But now look at boron. What block is this? This is the p block. This whole area is the p block. So how many elements in the p block are we? Well, we're 1 in. But what row are we in? We're in the second energy level. So we're 2p1. Then if we go to carbon, we're all of boron, 1s2, 2s2. But we're not 2p1. We're 2p1, and now we're 2p2. So carbon's going to be 1 electron larger there. And then if we go to, let's go over here to neon. So neon will be 1s2, 2s2, 2p. How many over are we? 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 is neon. And let's add up those electrons. So the s2 is 2 electrons. The 2s2 is 2 electrons. That's 4. Plus the 6 and the p, 2p, that's 10. And you'll see that neon has 10 electrons on the periodic table. So these are some of the electron configurations for some of the first few elements. Let's try a couple of longer ones down the table. All right, let's do one like silver. So silver is element number 47. All right, so we'll start at the top and we'll work our way down. So we're in the first energy level. We got to build silver from the first energy level up. So 1s1, 1s2. So we're the 1s2. Then we're going to go down here to the second energy level, 2s1, 2s2. Then we're going to go over to the right. We're now in the p block, remember. Over here is the p block. So 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. That'll make the 2p, all the 2p orbitals full. And then we're going to go down to row 3. And we're at the 3s1 and the 3s2. Because remember, this is the s block. So we have 3s2. And then when we leave the 3s, we're going to head over to aluminum. And that'll be the p block again, but we're in the third row. So 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. So the 3p6 is filled. And then we're going to go down to row 4. We're not at silver yet. Down to row 4. That's the 4s1 and the 4s2. So the 4s1, and the 4s2 calcium is 4s2. And then we're going to move over to scandium. Remember right here, this is the 3D area. So this will be 3D. And then how many in the 3D? 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. And once we get here, we start the P block. So that'll be 3D10. And then after the 3D10, we're in the fourth row, remember. Remember the D block is always down in energy level. So once we get back to the P's, we have to start the fourth. We're in the fourth row for the P's. So that's 4P, and then 4P1 gallium, 4P2 germanium, 4P3, 4P4, 4P5, and 4P6 is krypton. So we're going to finish 4P6 there. And then we're going to drop down to the fifth energy level. And we're back in the S block on the left side. So that's going to be 5s1 and 5s2. So 5s1 and 5s2. And then we're going to go to yttrium here, element 39. Now we're getting really close to silver. So if scandium 21, element 21 was 3D, that's going to make this 4D because we're one below it. And then 4D1, 42, 43, 44, 45, 46, 47, 48, and 4D9 is silver. So we're going to be right here, 49. And if you add up all these exponents, right? If you add up all the exponents that you see, the 2, the 6, all the way down, you're going to get 47 electrons total for 47 electrons that silver has. And so we know that's the correct electron configuration. Now, how many valence electrons does silver have, or electrons in the outer energy level? So what's the highest energy level here? So we got energy level 1, we got energy level 2, energy level 3, energy level 4, energy level 5. Right here, sorry, energy level 5 right there. And this is a 4 again. So the highest energy level is a 5, which means that's the fifth energy level away from the nucleus is where these two electrons are located, and that's the farthest away because everybody else is 4, 3, 2, or 1. So right here we see that silver in this scenario has 2 valence electrons. Now we'll learn later that actually what silver does is it actually moves one of these 2 electrons to fill this 4D9. And what it does is it makes it 4D10, and then it turns this 4D2 into, or sorry, this 5s2 into a 5s1. And so what you'll see is that sometimes elements like can do this where they actually will move or shift some of their electrons around because silver is so close to a 4D10 being filled, and it likes to have its orbitals filled up, either half filled or fully filled. So it'll fill up the 4D9 to 4D10, and then it'll be left with a 5s1. And so when silver reacts with other elements, it usually actually has 1 valence electron, this one right here, because of some of that shifting it just did. And so when silver reacts, it'll actually lose its 1 valence electron to become a positive 1 ion, and it always behaves like that. So when we understand electron configuration, we can actually predict the type of ion that the elements will form when they bond. So this is a little bit longer one. If you want me to do an F block one, we can do that in a later video. All right, so the last thing I want to look at was electron dot diagrams for like the valence electrons. So if you're in group number 1, you'll recall that if you're in group 1, you finish with an S1 configuration, So for hydrogen, helium, sodium, so hydrogen finishes with a 1s1 configuration. So for hydrogen, it's going to have one dot around its element to show that it's valence electrons. For lithium, lithium finishes 2s1. So it's going to have lithium with one dot around it. Sodium finishes 3s1. So sodium is going to have one dot around it for that 3s1. Potassium is going to have one dot as well because it has a 4s1 finish. And then 5s1 is going to be rubidium. It has one valence electron. So you'll notice everybody in group 1 has one valence electron, which is why they react in similar ways. Now, if you were to go over to, let's say, nitrogen here. So nitrogen's group 15. So this group. So nitrogen's configuration is, let's do it here, 1s2, 2s2, 2p3. So that's nitrogen. And then let's do phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3. And then let's do arsenic below it. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. So when you look at this, right, when you look at the valence electrons in the outermost ring, the highest energy level for nitrogen is the second energy level. And so it has 5 valence electrons. For phosphorus, the highest energy level is the third energy level. The other energy levels are 1 and 2. And so when you count it, it's got 5 valence electrons. And then for arsenic, the highest energy level is the fourth energy level. So this 3D is a 3D10, so that's a little bit lower than 4. And so if you look at those two, it's got 2 in there in the 4s2, 3 electrons in the 4p3. So together, that's 5 valence electrons. So everybody in group 15 has 5 valence electrons. So when you draw their electron dots, it's 1, 2, 3, 4, 5. For phosphorus, 1, 2, 3, 4, 5. And for arsenic, 1, 2, 3, 4, 5. I kind of crammed those in there, but they have the same number of valence electrons, 5 apiece. And so now we can say to ourselves, like, oh my gosh, like if these 3 elements are in the same column of the periodic table and they have the same number of valence electrons, then when they come in contact with other elements, we can expect them to react in similar ways as everybody else in the group. And that's what's really, really interesting about group 1. Like group 1, like I love this. Like sodium, I'm kind of go off on a tangent here, but like sodium by itself, pure sodium, has 1 valence electron, and it will, when you drop sodium in water, water will steal this 1 valence electron and it'll explode. If you have chlorine, so chlorine has 7 valence electrons, because it's in group 17. So chlorine will actually tend to bond by itself, or bond with itself. So it'll have like 6, 7 valence electrons. And then what will happen is chlorine will bond, it'll share these 2 electrons to make a bond to become Cl2, which is a molecule. And chlorine gas, Cl2, will kill you. It's poisonous. But if you were to bring sodium and chlorine together, and you understood the concept of valence electrons, you would see that sodium has 1 valence electron. Chlorine has 7 valence electrons. In order to be stable in chemistry, you need to have 8 valence electrons. So chlorine will actually steal this 1 from sodium. And when it does that, it'll take, let me see if I can get rid of this. It'll take it. And when sodium loses its 1 valence electron, it becomes a +1 ion. And when chlorine gains its 1 electron, it becomes a -1 ion. And then these come together, the opposite charges come together to form a bond. This is called a ionic bond. And they form a compound called sodium chloride, which is table salt, which we eat, and you can eat it. So sodium, pure sodium, will explode in water because it has its 1 valence electron gets stolen. So that's how big of a deal a valence electron is. Chlorine will bond with itself to get its 8th one by sharing electrons. That's poisonous gas. But when you bring sodium and chloride together, you make a compound you can eat. And I find that fascinating. So when you really understand the valence electrons from this topic, then you can apply it to chemical bonding in that later unit. So in chemistry, things build, and you really have to understand the early concepts to understand the more complexities in later units in the course.